Okay, yeah, we are live. Okay, so hello everyone. We'll get started in just a few minutes.
Ben, could you let Andrew back in?
Oh, okay.
He
Yeah,
accidentally clicked the wrong thing.
okay. Sorry, I didn't see the join.
Yeah, sorry about that. I got the little recording notification to pop up, and while I was typing, and it it selected leave chat while I was typing.
Okay, so around the hour, let's get started. So welcome everyone. We're very excited to have Strangeworks with us today. And we're also very excited to have Cesar Rodriguez, who is the Chief Scientific Officer at Strangeworks. He will be giving the tutorial or slash workshop with us today. We are also very excited to have Andrea Ochoa, who will be helping answer some of the questions in the chat. So make sure that when you do have questions, you can post them in the Twitch chat, and we'll have some interactions and there will be a very interactive workshop. So make sure you stay in the chat and ask all the questions that you may have. And afterwards, if you have some follow-up questions, you're welcome to post them in the Discord chat in the Strangeworks channel. And Andrew and Cesar will hop around later to answer any questions that you may have after the stream. And once again, this stream will be available on Twitch as a video on demand afterwards as well. So you can catch up on any parts that you may have skipped over or did not understand during the live stream. Wonderful. So yeah, without further ado, let me hand over to Cesar and look forward to hearing the talk.
Thanks, Ben. So, hi everyone. I'm Cesar. I am the Chief Scientific Officer at Strangeworks, and I'm here to give you an introduction to quantum industries in general, with a focus on quantum development. But the idea is that you have some big overview and have a place that you can play with some code and just get your first quantum programming experiences. Okay, so at Strangeworks, our goal is to humanize quantum, and for us, what that means is to lower the barriers such that people like you guys can get started on quantum computing. We believe that quantum computing is it should be from the ground up, community driven, and even though it's very early in its formation, the more people, the merrier. It's going to really help the industry. The goal of today's talk is to give you a feel for what is quantum computing, where's the power of one kind of algorithm with an actual example, but it's very, very visual. But also at the same time, in parallel, I want you guys to get some coding experience. You don't have to you don't have to know a lot about coding, as long as you're not afraid of commenting code and doing some copy paste. It should be fine. It should be fine. So I encourage you to please follow along as I give the different examples. And you can see here that we have quantumcomputing.com. That is our community website for Strangeworks. And if you go to quantumcomputing.com/tutorial, you can sign up, create an account. This is all you need to do to get started running some code. You can do it on the browser right there. So I encourage each one of you to go there, create an account right now, and throughout the talk, I'm gonna be giving you some examples that you will find there such that you can place with some quantum code. This is the Strangeworks headquarters. Our headquarters are in Austin, Texas. We also have a German office. And
Cesar, sorry to interrupt. It seems like the slides look a little bit glitchy to everyone. Maybe you can replay it.
Okay. I will do that now. Okay. Maybe 1 sec. Okay. So. Okay, is it better now or?
No, I think it's still. I think it's only taking up like part of the screen, and there's like a ring of like the original screen around it.
I see. Let me see if I can change something here. Give me 1 second. Okay, let's see. Is it better now?
Yeah, that's perfect.
Okay, great. Yeah, so this is our headquarters in Austin, Texas, and if you're ever by there, please come visit us there. So just to give you an idea about what quantum computing is, quantum computing is the biggest revolution in computing since computing started. Like this is not an exaggerated thing. Aristotle would totally understand the basics of how one of our current computers work, but he wouldn't understand classical quantum computers. He will understand the iPhone, but not quantum computers, because he uses a very different logic. Quantum is our reality. It just happens to seem strange because our brains are really good at thinking in terms of classical information, zeros and one bits. These are just like a small part of all the quantum information that's out there. So quantum computing is really about using the rest of this information that's out there in the universe to do more powerful computation. In this talk, what I will do is I'm going to answer 5 questions. What is quantum? Why is quantum? Where is quantum? Who is quantum? And when is quantum? So that is like, what's quantum information? Why is quantum computing so powerful? Where to do quantum computing? Who is a quantum developer? And when do you start for that? And to motivate why need quantum computer, I'm gonna discuss a little bit of the state of the art. So here we have like HPC, GPUs, all these things. Even my phone itself, we're gonna call all these things classical computers. And of course, they're very powerful. We can talk right now through that because we have them. However, they are not very well suited for some kinds of problems. These tend to be some problems that when maybe you have a lot of data, you process something, you find an answer, and then you have one more data point. And just by adding one more data point, this becomes exceedingly harder to do, like big network problem, and you add one more node to the network. Then you add another one, and then it becomes even way harder, and so on. So these kind of problems, they might not scale properly. So there's a bottleneck, and especially now that we have so much data, data is growing faster than classical computers could follow them, even if they keep growing. This is a limitation of classical computers. Quantum computing is a different way to do computing that is just starting now. We are at the very early stages of this industry. And a lot of people always ask me, how much faster is quantum going to be? And in some sense, that's like the wrong question, because it's like asking how much faster is an airplane compared to a train. And yes, airplanes are way faster. It can be way faster than trains. But that's missing the point, because the point of the airplane is it takes you places that the train couldn't take you. That's really it. And here in Europe, for example, we use both. We use trains to get to airplanes, to get to trains, and so on. And this is really how you should see things, that quantum computers and classical computers are going to work together. And when a problem is very well suited for a quantum computer, the classical computer will pass it on to the quantum computer. Depending on who you ask in the industry, you're going to hear some pessimists that say, oh, quantum computer is going to be useless for the next 20 years. Some people say in 3 years, we're going to have practical applications that are extremely valuable and enterprises are going to buy. And the truth is, like, we don't know. That is the absolute truth. We do know that the impact is going to be very large, but we don't really understand. We don't really know when these things are going to reach that moment where everything becomes practically valuable. However, what we do know is that because it's so different to program quantum computers, we need to prepare earlier. Mostly because this is it's going to be a bottleneck of people and so on, that we need to develop this workforce and so on. So people like you guys, you're doing the right thing by attending the seminars, the seminar series, which is to start preparing for that future. When these things happen, we need a big workforce of programming these quantum computers. Quantum computers are going to have an impact in many industries: pharmaceuticals, optimization, finance, logistics, data science, cryptography, search, machine learning, and so on. But this is not the only places it will be. There's going to be a lot more. Quantum computer is not magical either. It's not like it doesn't make everything better, but it just happens to be really good at some problems in these things that happen to be important problems. So I'm trying to give you guys a very measured, optimistic view of what it looks like. And to do that, first we have to dispel a lot of myths. Like if you go to Google News or something and try to look at something for quantum computing, you're gonna see a lot of absolutely nonsensical titles and stuff that makes no sense and so on. And this is because it is hard to explain how quantum computers work, and it's hard also for newspapers to explain how these incremental steps that we're doing towards make them practical, how they contribute to each other, because they're very technical. So what I'm going to try to do today is give you a very concrete overview of the whole industry, and give you also some sample code so you can play with code with some of the basic concepts without any equations whatsoever. And so to do that, first I'm going to give you a little tour about hardware. If you Google quantum computers and you go to an image search, you're going to see a lot of these things. I think this is Google, Rigetti, IBM, D-Wave computers. I think they look pretty cool. These pictures here. And you'll see them over and over being used in pictures like this being used in all the news articles. However, these are not actual quantum computers. These are the cooling systems for quantum computers. They look awesome, I think. They look like steampunk stuff. But this is the actual chip. This is just cooling. All these things here, this is cooling. All these cables here, this is a marvelous to see. Like, this is just how can you bring all these things together here to cool something down here in the middle. And you can get a sense that it's quite crowded there, that people are putting a lot of work into cooling this properly, and it's pretty crowded. And this is one of the limitations that we have on quantum computers, that quantum information is very fragile, and we have to cool it down a lot to preserve it. But now you guys know, whenever you see a picture of a quantum computer that looks like this, you know that's not a quantum computer. The quantum computer is somewhere here. These are the cooling systems. So think of this as if somebody was asking, show me a picture of a microchip, and instead they show you the picture of the fan on the computer. This is really what we're looking at here. And the question is, why do we have all these different ways to wire them? Why are there so many hardwares? Which one is the best? This is something like everybody wants to know. Just tell me which hardware is the best, and I'll just use that one. And the truth is that none of them are good enough yet. And the reason is because since quantum information, which we encode as qubits, these are quantum bits, qubits, is very fragile. And we haven't figured out a very good way to keep them from losing the information too fast. So we have to do because the information is lost so fast, we can only compute certain kinds of things. And this provides some limitations of the kind of things that we can do. Ideally, what we would like to do is have a computer with a lot of qubits, and that you can connect these qubits, all of them together very well. And all the qubits are very reliable. That will be what we would like these three categories to be very good at. Nobody can do all three well. That is the truth. What each company is doing, though, is doing different compromises on these things. Maybe sacrifice some connectivity for qubits, maybe sacrifice some reliability for more qubits, maybe sacrifice qubits to aid the reliability to have one qubit support other qubits. This is known as quantum error correction. And this is what all these companies are doing, is really trying to strike a balance, a compromise between all these things. However, what we hope to gain from this is at some point, one of these companies is going to find the right balance between all these parameters. They're going to improve everything enough that it's good enough in all three, and then it's going to be scalable. This is what's known as scalable quantum computer. When that happens, we will say, now we can give you predictions of quantum computers are going to be this big by this year. In the meantime, whenever you read an article and they just say number of qubits, know that denominator tuning is meaningless. Because I myself, my body's made of quantum information too. I have a lot of qubits in my body, and I'm not a quantum computer. So keep that in mind. That qubit counts don't mean anything. What matters is these three parameters together, and it's quite complex, their relationship. And the image I want you to go home is like with this human towers here that we have here. And you can see that there's different strategies between them. Some are really impressive, but clearly don't scale. Some, I don't really know what they're trying to do here. Some seem to have some sort of system figure out, but we're not there yet. It will be inconceivable for us to imagine a human tower so large that gets to space or something. We know that that's not scalable. However, we do think quantum computers will figure out this right balance and this right strategy to get there. Now, changing the topic a little bit to software. There's a lot of software packages. I will not talk about them all, unfortunately. Just this is a gigantic universe, but I want to mention some big ones that are good entry points for beginners. And this is IBM Qiskit, Google Cirq, Rigetti PyQuil. These are all Python based. So if you know Python, you'll feel very comfortable with them. And they use Python to write quantum assembly language, is what's called. And that will be QASM. So QASM is like a low-level way to encode quantum circuits. All these things are basically big Python libraries to do this with a lot of additional applications. Microsoft Q#, I want to mention also, because that's a very high-level language that looks very, very promising. However, right now, because of the limitations in hardware, a lot of the people prefer to work with these low-level languages that are a little bit closer to the quantum computer itself to optimize things. And there's a lot more, like there's like machine learning applications and a lot of chemistry tools and so on. Now, of course, you can stitch together to do useful things. What we hope with our community at quantumcomputing.com is that we can help you guys start playing with all of these things and put something together. However, one of the challenges is that if you go look at these websites, these are very mature languages, all of them. They're changing all the time. They break compatibility constantly. Like every few weeks, there's going to be some upgrade, and they're going to break compatibility fully. So this makes it very daunting, not just from the fact that you have to learn quantum physics to do it, but also because the software, it's at a very early stage. And so what we're trying to do in quantumcomputing.com is to make it easier for you guys to keep up to date with the latest versions without having to do the headaches of the updates and the dependencies and all that. Just make it very easy for you guys. And quantum computer has some problems. There's multiple barriers to entry, and I like to categorize them in three layers. Is that one is limited access. It isn't so easy to get access to all the quantum computers out there. You can access some. There's some limitations to what you can access. There's some that are not accessible yet for general users. And also simulators have a lot of limitations. There's a lot of stuff you just simply cannot do in simulators. Although simulators do have teaching value, of course. The second big challenge is that there's not a quantum workforce. Even if we had a really large quantum computer right now that was scalable and very powerful, we don't have enough quantum programmers to make the best out of it yet. So this is where you guys come in. And finally, is that it's a long-term play. This is not a trip to Puerto Rico. This is a trip to Mars. So people have to be have very measured expectations that it's going to take a while before the things are applicable. And if you take all these things together, it can be very confusing to get started. And everybody asks, where do we begin? Just tell me which software to use, tell me which language to learn, and tell me the hardware, and I'm done. And the truth is, I cannot do that. I cannot do that because everything is changing. And what's exciting is really to learn what is the new things that are coming out. What are the improvements going on? This is the stage we're evaluating all these tools, all the software, all the hardware to incrementally do it better. And what I really believe is that with a community-driven approach, we can all help make this process faster and better. So given this big disparate universe of quantum computer, what I want you guys to do is to go to quantumcomputer.com and sign up. Go to quantumcomputer.com/tutorial, create an account, and start playing with code there. I will guide you some examples today. I'm going to motivate them with like some conceptual ideas. But the idea is that just on the browser, with you having to install anything, you can start playing with a lot of the languages. The ones that we don't support yet, we will support soon, and you can always give us feedback to the ones you want to prioritize. But we have the biggest palette of languages that you can have, and also you will see our hardware partners that we're going to be unveiling hardware access to their different machines little by little the next few months. So the main point of this talk is that I really believe that you guys can learn quantum computing by programming a quantum computer. This is not very surprising in some sense, but a lot of people think like I'm a quantum physicist myself, and I learned, of course, I program quantum computers with pen and paper and doing matrix algebra. However, before I was a quantum physicist, I used to be a software engineer, and I didn't learn it that way. I did learn truth tables, of course, but in the end, you learn by programming. And I think the same is true here, that there's a lot of value to be gained by having access to code very, very early and trying to put it together with the other things. So today, as I give you explanations, I would suggest that you guys play with some code. The links are here in quantumcomputing.com/tutorial. And I will tell you, okay, go play with this example and so on. And I want you guys to really just play with the code. A lot of times, we're going to ask you to comment the line, uncomment the line, copy paste lines around. The idea is that you get a little feeling that you're controlling something in the quantum computer for real. Okay, so with that out of the way, let's do some quantum physics. So this is my favorite beach in Puerto Rico. This is called Mar Chiquita. And as you can see, there's a rock barrier, and the Atlantic has carved a little slit here where the waves from the Atlantic Ocean comes right through to create this beach. If you look at this rock here, I like to sit here when I go home, is that you see the waves come through here. And as they pass this hole in the rocks, this slit, it creates a perfect semicircles of this wave, which is what shaped this beach to be so beautiful here. And this is a really good place to do physics, by the way. And if you have a bottle of rum like me, that doesn't hurt either. And however, when you start thinking about that as a physicist, the next thing you always ask is, what would happen to these waves if I added a second slit? If the beach had carved a second hole, how would these things look like? And this is known as the double slit experiment. This is one of the foundational examples in quantum physics. So imagine now that this is the rocks, and these are waves coming through them. How will the wave patterns look like? So as the waves go through each slit, you're going to see each one is going to radiate as a semicircle, but then the semicircles are going to interfere with each other. That means that the peaks are going to add up. The valleys are going to subtract, are also going to add up in the other direction. So you're going to have a lot of highs and lows when this happens. And if you had a board close to the end, and you start to measure where are the peaks and the valleys of these waves, you will see such a pattern like this. You see where it's very dark, this means it's very high, the wave, and it's very light, maybe it's very low, the waves. And you're going to see that there's some places that this constructively or destructively interferes these waves together. Now, since we're doing physics, we can ask the same question. Instead of sending waves, what if they send particles? So picture them as bullets or something. So you have a machine gun here, you're spreading bullets through this. And of course, if you do this, most of the bullets are going to bounce off the wall, but some will make it through the slits. And they're going to create two, patterns here, like some roughly in this area here, and others bunch up here. Roughly speaking, one here and so on. So the waves and the particles look very, very differently. However, what if we sent a really, really small particle that was in the quantum realm? I think of it like a photon or an electron, something that is quantum, but we think of it as a particle. If you send one of those through here, what happens is that this quantum particle actually goes through both slits simultaneously, interfering with itself and creating this pattern over here. So we send one and we get a click here. We send another one, we detect it here. We send another and so on. But when you look at all of them, although each one is, there's different uh, um, footprints of where this particle landed. The whole pattern looks more like the wave pattern. So it looks like a wave pattern made out of particles. And this is because each particle is a particle. They go through both slits, each of these quantum particles. They go through both slits simultaneously, interfering with itself, but then it's detected again as a particle. So it does have properties of quantum objects in this sense, both particles and waves. The fact that this particle goes through both slits at the same time, it's called quantum superposition, because you cannot say went through one or the other, it goes through both. And quantum superposition, it's always like, it's the iconic example of quantum that it seems very, very abstract and very difficult to wrap your head around. And I just want to point out that the reason why it's so hard is our fault as human beings, because our brains evolved to be very good at thinking about saber-toothed cat. Our brains are not very good to think about a Schrodinger's cat. So saber-toothed cat, you can think of in terms of classical information very well and try to escape from it. Schrodinger's cat, you need to know qubits and so on, and our brain just didn't evolve for that. So this is really why it feels so out of place. It's really our fault as human beings. And one way that I would like for you guys to picture this, this is an image you should have in your mind, is that this difficulty that we see the world in the classical world, but the quantum world is larger. So whenever we try to study a quantum problem, we're taking this larger space and we're trying to represent it in a smaller space. And this is incomplete. This is the same as trying to take a 3D object in a 2D plane. So like, for example, if we have this wireframe, if I tell you, oh, this comes from a 3D object, by the way, your brain might sometimes look at it like a box, like here with this in here. Or your brain might actually look at it like a corner in this here. And in fact, sometimes your brain like looks at it one way and then it flips it and like back and forth, and you get a headache, and it plays perspective tricks with you on you. And the reason for this is, of course, is that it is incomplete to describe a 3D object in a 2D plane, a piece of paper. It's just not enough information for your brain. Your brain is trying to make sense of it, and it makes no sense. And it's just like, wait a minute, both are encoded in the same place. And it seems very, very puzzling, when in reality, if we have access to the 3D world, this will be very clear. And it is the same with quantum information. The quantum information is very larger, but as we study it only using our brain that only understands classical information, we only see some aspects of it, and it seems contradictory. It seems like it's doing two things at once and so on. But that's really our fault as human beings. However, the good thing is that you don't have to learn a lot of mathematics to start playing with this. You can actually use code to play with this. And for this, I'm gonna ask you guys to go to the example that's play with One Qubit. If you haven't done this, what I recommend to you to go is you go quantumcomputer.com/tutorial. Here we have the welcome, and you can sign up for the platform by clicking here. You create a username and all that. And here I have a list of the examples I'll be using for this talk. The first one is play with one qubit. Okay, so I have an explanation here. This is I will talk about this in a second, but the idea is that this is stuff that I encourage you to play right now. But also, if you want to revisit it later, and I hope you do, because you will get a lot more from it, you can come and just review all the things that I was talking about. And this is a very simple example of how do you take one qubit and do some quantum operations here. So what is a qubit? A qubit is a two-level system, so it's zeros and ones. But unlike a bit, you can be in quantum superpositions between them. Sometimes people say that it's both at the same time, but it's not just that it's both. It can be many different kinds of both, and all those kinds are what we call a quantum superposition. They'll look like this. We have parameters here, so you can tell how much of each is. One way I like to for you to think about it is that if 0 is the south pole of this sphere that I'm showing here, let's see if I stop the share so you can see it bigger. Okay, so if 0 is the south pole here and 1 is the north pole, So classical information is like you're doing computing with one point here and one point there. And quantum information is you're doing computing with the whole sphere, with all of it, even inside, by the way. So when people say, oh, it's in a superposition, it's not that it's in the North Pole and South Pole at the same time. It's that it might be in the equator, or it might be over here in California, or something like that. That's really, it is everywhere on the surface. And of course, you can think of it as this parameterized that in some way, sometimes the state can be in the North Pole or the South Pole. And it's the same with qubits. This is the block sphere representation for qubits. You can see here. And this is the same thing I was saying, that we say it's 0 when it's at the bottom. It's 1 when it's here. But the quantum state can be anywhere around this, represented by this vector. Everywhere parameterized. This alpha and beta parameters are just the parameters to tell you where the vector is. However, what's interesting is that in quantum physics, we cannot look at the whole sphere ever. We can never see the whole thing. We can only, whenever we look, it just gives us some probability if it's on the North Pole or the South Pole. This is the part that's very puzzling. This is what I was saying, that it's like it's incomplete representation of the quantum reality. Such that if it's in California, maybe sometimes it tells us in the North Pole when we check. Sometimes there's in the South Pole. It never tells us in California. But if it's maybe tells us a little bit, like if we check many times, it tells us it's more likely to be in the North. So it's probabilistic. If it's in the equator, maybe tells us half. Half of the time it says it's north, half of the time it says it's down. And this is the main challenging thing to understand quantum physics, is how does this quantum state representation, how does it connect to the probabilities? And what I'm going to do is I will show you some examples of the most common gates here, and then you guys can play with it a little bit. So remember, quantum qubits, they're zeros and ones. They are represented by this block sphere and probabilities. And operations on a qubit are basically rotations of this sphere. So it's really like rotating things around here. So you can do a rotation, that's x. So if you have the x-axis, the x rotation will be really moving this around 180 degrees by the x-axis. That's one of the simplest operations, one qubit operations. The y will be the same around the y-axis, and the z or the z-axis will be the same around this one. And think of this as sort of logic rules, but they're a little more interesting because we are not using classical information. It's not true and false, it's qubits. And the last one is the Hadamard Gate, which is a combination. You can sort of see here this matrix has this one here mixed in with this one here. And this one is represented by two rotations, two partial rotations. It's just a combination. People like to write this one. They're not unique, but it's a very common one you'll see over and over in many gates. So what I want you guys to do now is to go to this example again from quantumcomputing.com/tutorial and click here, run code. And here you will see your first quantum program. This is written in QASM. QASM is, as I said before, is quantum assembly language. So it's supposed to represent a very low level representation where you're putting quantum gates. So these are like the quantum logic gates. You're putting them together. I include one library, this is the basic stuff. And the first thing I do is I'm creating a one qubit. This is a register. So you say, oh, how many qubits do you need for this example? We just need one, so we create one. And also I'm creating a classical bit. The reason is, remember guys, that our brains are used to looking at classical information. So we're always gonna take the qubit and then try to pass it on to the classical bit somehow. And then here are some of the gates that you can do. For example, Z, X, Y, H. These are the ones I mentioned before. But if you want, you can run this. Let's run it one time. Okay, let's see what happens if I put this. So we started with a qubit. Okay, so let's see what we have here. So this again is quantumcomputing.com, and this says this program took 4 seconds to run. It was run by me, and it's completed. And the framework was it was a QASM language, But it's the QASM language inside the Qiskit simulator. So Qiskit writes QASM, and we're using this one here. The provider is Strangeworks, so that's us. This is running on a simulator in the cloud that we host. So if you guys want to run some stuff, do some simulations, this is for free. This is open for you guys. And we ran it one time. So what we did is we have one qubit. We did a Z rotation. And then we have a barrier here. The barrier is just a way to visually separate where things are. So think of it as the quantum circuit. And then this is at the end, the quantum measurement. We're actually looking at the outcome of this qubit. And then we store this information in this bit. So as you can see here, this says that this qubit is 0 100% of the time. Not very exciting. Not very exciting. However, remember I told you this was probabilistic. So what I want you guys to do is try this again, but instead of 1, maybe try 10 or 11 or 20, something like that. Try to do a few more. Just run a few iterations so you get some probabilities. And it's still 100%. So we know for sure that this is on the South Pole all the time. 10 out of 10 is on the South Pole. So what I want you guys to do is maybe add some more gates, maybe uncomment some of the slide by deleting the slashes. Let's see. And run the code. Let's say run it about 10 times and so on, so you get some good statistics. Okay. So you see we did a Z gate, the Y rotation also, and then we did the quantum measurement. Now it's 1. It's all the way to 1. So this Y rotation moved the South Pole to the North Pole, essentially 100% of the time. And you can go a little crazy here and just try a bunch of them. Let's see here. You see, we're controlling this qubit, and now before we got all the way to 0, I show you how to move the 0 to the 0 to the 1. But now we start having superpositions where sometimes it's in 0, sometimes it's in 1. And what I would like for you guys to do is right now, just go play with this, mix and match some of these, change the order of the gates a bit too, if you prefer, and run it always about 10, maybe 20 times, something like that, just so you get a feeling that you are controlling your qubit, that you can change things a little bit. It's not gonna be like suddenly you understand how to do all the qubit calculations at once, because this is really like learning a new logical system, and you have to do a lot of practice to do it. But what I want you guys is to sort of not be afraid of playing with this. And if you have any questions, that will be a really, really good time to open the floor for some questions before I continue for some of the examples. Like, please, guys, play with this and send us some questions.
Cesar, someone in the chat asked if you could make the window bigger.
A little bit bigger?
Yes, please.
Okay. Yes. It's everything or just the code, do you think?
Maybe the code.
Okay, perfect.
Yeah.
Awesome. Thank you very much.
So it looks like we have a few questions in the chat.
Okay.
So someone asked, why does applying a Z and the X gate have the same effect as a C naught?
Say it again?
Why does applying a Z and X gate have the same effect as a C naught?
As the C naught?
Yeah.
It's so C naught. I will introduce C naught gates in a little bit. C naught gate is a 2-qubit gate, and X and C are 1-qubit gates. So in general, it will not have the same effect because one only changes 1, the other one changes 2. However, if you look at partial parts, indeed, it might be that in some cases it looks similar, but if you explore it further, you're gonna notice the differences. So the main difference between the C naught gate, which we'll introduce later, and X, Y, Z is one is for 1 qubit, the other one is for 2 qubits. So of course, you cannot do anything with one qubit. This example that I'm doing is very trivial on purpose to introduce you guys. We'll get to those in a little bit, and maybe we can play a bit more with the CNOT gates, and it will become more clear in one of the next examples.
Someone else asked, what is the barrier doing?
That's a very good question. So what the barrier is doing here is, I'm going to share it again. What the barrier is doing here, you see it here. What the barrier is doing here is just making it visually separating this part from this part. If you want to play with something, you can add more barriers here. Let's see, I'm going to copy this. I'm going to put it here. So it's just for visually grouping things so they stand out more. Now I'm putting a second barrier here. So you see now we have the first group, the second group, and the last group. It's really for that. For one qubit, it's not so important. It's when you have a lot more circuits. Sometimes the compiler tries to optimize things, and in doing so, they become visually very ugly. So use barriers to make sure it doesn't mix things through the barrier here. So for now, think about it as just a visual remark on that this one happens first, then this two, and so on, so we can find things easier. I like to use it at the end always, so you can see that the whole circuit happens, and then at the very end you do the measurement. Yeah. Any other questions?
Yeah, someone asked, does the arrow symbol mean superposition in the circuit diagram?
Here? No. So that's an excellent question. So this is a quantum measurement. So this is until here you have all quantum information, which is the sphere, and then when you do a measurement, you get a probabilistic outcome. So if you get superposition, sometimes you get up, sometimes you get down. Each time you want to see, like you do it once, you say, okay, it was up one time, and this arrow means you take the quantum information, you find the probabilities, and you put it in this classical bit. So this will be like, okay, first time it was up, you write it here as a 1 in the classical bit. And here what we're reading is actually the classical bit. Then we do it again. Next time maybe it's down. And we put in a classical bit and we read it. And we keep a tally of things. And this is how you build up this histogram. Is the arrow just means look at the quantum information, write down the classical information you learned from it. Is that clear?
Someone else asked, why does it need to include QE lib 1? Is there a QE lib 2, lib 3, etc.?
Oh, so why is only one qubit here?
No, I think they're talking about the include part where you have QE lib 1. Oh, I think that's just how you guys do the library naming system. Right?
Yes, this is a standard library, so the outputs and the inputs and all those things look nice. So this is just a standard library that you call at the beginning. So you can make the outputs and inputs just look great. That's basically it. Yeah. It's just the boring include files that you do at the beginning of programs. This is the basic ones. Of course, you can add a lot more. I just wanted to keep it basic with the most minimum one. Yeah.
Yeah, I think that's all the questions we have. So, we're getting a couple more now.
Yep.
Someone asked, what are the inputs for the rotations?
That is an excellent question. So I already told you that the X, Y, and Z, they already defined the 180 degrees above this axis. However, if you see here, I have some other gates here. And this is a rotation on the X axis by 0 degrees, but if you want, you can make 10 degrees. 10 degrees here. So you can start mixing and matching these things. So I have this. Okay. So I have now this one here. This is a rotation on the axis by 10 degrees. Let's see, 10. Sorry, not by 10 degrees, by 10 radians, I think it is. Yeah. Yeah. I made a mistake here. Probably have a, let's see. What am I missing here? Let's see. Okay, yes, it's the radians here. It should have pi. Let's write it nicely here. That's better. And it should be acting on one qubit here. That's the part I'm missing. There we go. Okay. So if you want to parameterize this rotation, the other gates are those below. The idea being, you see now we're doing partial rotations and so on. And if you change this number a little bit here, you're gonna get different things. And so the idea being is that the X, Y, Z, Hadamard, they're presets, and they're very common ones that you will see over and over and over in logic in quantum logical circuits. And below are the freer ones. Of course, these ones from the beginning, they are constructed from this under the hood. That's what they are. And there's some additional ones that I'm not gonna have time to explain, but I did wanted to put them here because you might find it in some circuits, and it gives you an opportunity to go play with it. You can look them up in some of the resources that we have here. We have a really nice list of quantum computing resources here. It's very extensive, and so maybe that's also a good place. So this was just to say that I wanted to give you guys a simple place to start, but there are other options for you guys. Yeah.
So if we have one more question, time for one more question, maybe. So someone asked, how are the qubits getting composed? I don't see any operators.
Yes, that's a very, very good question. So by default in QASM, when you create a qubit, it is in the 0 state. So it's in the south pole always. This is just like saying when you define a memory, it's 0. And this is just a convention here. So that means that if the qubit is 0 and you're like, I need a qubit 1 because that's the information that I want in code, you have to do an operation first to get it out of the 0 state to encode the information that you want. You have to do some operations. This is why this is an important first example, because it's about taking the 0 qubit to all the other qubits that you might want to encode, which of course depend on the problem. This is the information. So think of it as like by default, the quantum memories are 0, and then you do some things to write down the information. You do these operations here that are here to take it to the state that you want to actually get things started. So here you haven't started anything. This is just preparing the memories the right way. Yeah.
Yeah, looks like that's all the questions. There's some other questions that I think already been answered in the chat. So yeah, I think.
Okay, that's fantastic. So then since you guys hopefully you guys play with this a lot. I already show you this. Let's go to the next one. I want to give you one little puzzle that I call solve this Rubik sphere. So I told you about that the qubits are represented like a sphere, and the Rubik, of course, is this cube here. You know that you do rotations and to scramble, and then you try to descramble it. This is the standard game. This is a Rubik's cube. So this is a pun. It's like the Rubik's sphere. And this is our next example. The idea is you already learned some of the basic quantum operations for one qubit. You cannot do any computation with just one. You need a lot more. But as a learning tool, well, what I want you guys to do is to do some rotations to try to get to the state, to a particular state. So let me show you how that looks like. So I took one qubit and I prepared it in some ugly state. So I did a lot of rotations that are like all over the place. And your goal is, can you make this state point to 0 100% of the time? That is the challenge for you guys. So I prepare a state. Can you use controls to move it down? Of course, this is not as trivial as it seems, because you cannot see the full qubit. You can only look at probability. So you cannot fully look at the state. So you have to do some trial and error with this. And I prepared some code here for you guys. It's again, if you go to Strangeworks, the quantumcomputing.com/tutorial, solve this Rubik sphere. It explains here. I spun the qubit in also direction. Your goal is to make it point down. And if you click run code, here main QASM, you will find the code. Let me walk you through it. So again, this is QASM 2. This is the assembly language that we're using with the standard libraries included. We create again one qubit and one classical bit. And then this is me scrambling the qubit. This is me trying very, very hard to do some rotations like this, but not letting you see it, like making it like trying to make sure that you didn't follow every single thing that I did. If you guys want, you can actually calculate these matrices and multiply them, and you will figure out what I did, and it's not so hard. That would be the easy way. Or the hard way, depending of how much you like math. However, what I want you to do is like, just don't look at this too much and continue here. So we can do the puzzle properly. So even though I did this scrambling, and I'm gonna run things here now. So I'm gonna run the code. Let's say I suggest you do about 10 iterations for this so you get enough statistics. So this is the weird scrambling I did. It's a weird rotation along a few different axes here. And you can see in the probabilities that it's like 60%, 0, 40%, 1. So it is somewhere like, it's somewhere kind of in the middle. Your goal is to apply additional operations here such that you make it point to 0 100% of the time. And I suggest that you only use these operations I provide here. It's the Z, X, Y, and H. So for example, this will be me applying set operation. I'm gonna run it now. You need to do about 10 or more so you get enough statistics, because otherwise by luck you might get it to point down. But if you have enough statistics, you are more certain that you found a solution. So I'm trying, what happens if I apply a set rotation here? Oh, something changed. Clearly something changed. Now they seem to have flipped, but I'm still not where I want to be. What I want to be is make this one 100%. And now it seems like I'm going in the wrong direction. So yeah, then maybe we can try something else. I can comment this one. Maybe try the Y rotation instead. I'm going to do it again 10 times. Okay. Oh, not there yet. So what I want you guys to do is start playing with all this a little bit, all these things here. And I'm going to give you some until you try to get it to 0. So I'm going to give you some tips here of what you need. Remember always to use about 10 iterations or more. Although there's a lot of gates that you could do for this problem, I made it so you only need a combination of X, Y, Z, and Hadamard. So it's only some of those that you need. You don't need to do all the other gates. So you can take those, comment, uncomment them, copy, paste them, change the order, because the order makes a difference in quantum gates. And finally, although it seems like it's very hard, I made this problem so you only need 2 gates of this, X, Y, Z, and Hadamard, using a combination of those 2 in the correct order. So it's not so many options. So you can just by trial and error try to figure out what was that mysterious operation I did and undo it. Again, use X, Y, Z, and Hadamard gates. Copy paste them around the code, and you just need two of those gates. So if I leave here, you only need some of these 4 here. Maybe if you want, you can move this one here. Let's see. Let's try different orders. Let's try this one here. Click run, 10, and you click run and see what you get. See if you can get this to point to 0 all the time. Oh, I did it. That was a solution to it. And what I want you guys to see is that if you can find other solutions to this, the solution is not unique, which means that there's many correct solutions. If you guys find a solution, your solution, and you want me to have a look at it, by the way, you can go here to share, publish. If you click here, this is a public link, so you can put this on Twitter or something. Look at me, I play with One Qubit. This is my code, and people can come join this platform, run the same code that you did. This will be public. But also, you can add collaborators. So you can just write my name, Cesar, and if you click send invite, and it will invite me to your project so I can have a look at it. So I can see your code is correct or so on. So I encourage you guys to play with this and send me your different solutions to this. Are there any questions? This might be a good time to let you guys play a little bit, and we open it for some questions before we take a break. Yeah. Are there any questions?
So it looks like everyone's jumping in to play around with the code.
Yeah,
Um,
perfect.
I think there were some people who are speculating what the answer is, but maybe we can keep
Yeah.
that,
There's more than one answer. So I want you guys to find the other answers also. Yeah. And if any of you guys get it, you can type in the chat, I got it, send it to me, and so on. In the meantime, as you guys work on it, I wanted to point out that we have a library of many examples and many posts with like teleportation. Some are written by us, some are written by some of our partners. And if you write some cool code, you can submit it to us, and we will add it to the library. Just send us some feedback, and we can add it here if it's good. The idea being that everybody can come and collaborate and learn from each other. We also have a list of all the hardware partners that we have, and we're going to be adding connectivity to this, so you can actually run this in real hardware instead of simulators. And for the projects, we support importing from Git. So if you find examples on Git, you can add them. You can, of course, start from the library, or you can start a new project. And I just want to give you a sense of all the platforms that we support. If you click here, add file, we can see that we support basic Python scripts, Jupyter Notebooks, OpenCasm, Forest, Penny Lane, Google Circ, Microsoft Q Sharp, BlueCat, IBM Qiskit, Deviation, Amazon Bracket, Project Qt, and a lot of other projects. So we have a lot of examples. You can just click on one, and it will have a template file added to it, so you can start playing with some code in different platforms. You can try many of them. And also, when you create a project, you can, if you find some good, if you want to try from a new project here, let's test again, test 2. You can upload files here as well. So you can drag and drop files from your desktop. So you can keep all the codes from all the different platforms here. Has anyone succeeded at solving the project problem?
Looks like there were a few answers.
Awesome.
So I think in the beginning someone said the answer is H gate, Hadamard Gate, followed by a Y gate.
Yeah, that could be one of them. There's others too. And in fact, something fun to do if you solve it is to try to find others, and this gives you a sense of how the different gates relate to each other. How you can do some rotations and you end up being in the same place. Like it's if you do this and backwards, you end up in the same place and things like that. So.
Right. Someone else said a long but stable answer will be to reverse the gates and make the circuit symmetrical. That way you get 0 as an output.
That is very true. That is a way to do it. So this is why I have to ask you, please don't do that. Try with the other ones. But if you want, you can always check that way. So the idea is, can you take the messy code that I did here and undo it using this limited gates? But if you let go of the limitations, that will be, of course, the best way to do it. Just cut and paste and just put negative signs everywhere and just undo everything I did. Yeah. That would be like taking the Rubik and peeling off the stickers and then putting them back in. That does work, yes.
Okay, yeah, I think people are also adding others as collaborators.
That's fine.
Looks good. Yeah.
That's great. That's
If you want to, so currently you cannot post links in the chat. So you can private message someone else if you want to, share your code to someone else or something like that. If you have a link that you want to share with everyone, you can message me first, and then I will make sure that it's okay, and then I'll post it on your behalf.
sounds good. So, Ben, will this be a good time to have a 3-minute break or something, you think?
Yeah, I think so. Right now we're on the hour, so why don't we all take maybe a 5-minute break and then come back at 5 past, and at the same time people can still kind of like try out and play around with the code.
That's perfect. That's perfect. Okay, guys, see you in 5.
Okay.
Okay, so I'm here. Ben, let me know when it's a good time to continue.
Yeah, I think we're 5 past the hour, so we can continue.
All right, perfect. Yeah. Okay, guys. So far, I give you an overview of quantum industries and also some basics of one qubit. So you did your first one qubit operations in simulator. And I encourage you again to go to the quantumcomputer.com library, find code there, run it, break it. That's how one learns coding, is by breaking code. One doesn't learn coding by coding, one learns coding by breaking code and then on breaking it. And so now we're gonna go to some other concepts, and this one is called quantum entanglement. I'm sure many of you guys have heard of it. And then we're gonna get to our first quantum algorithm and where does the power of quantum algorithms come from. So all right, I'm sharing my screen. Does it? If there's any issues, please, Ben, let me know. Yeah. Yeah. Okay. So this will be for the project called "For Whom the Bell Entangles," and this will be a pun, of course, about quantum entanglement. And quantum entanglement it's a very special kind of quantum correlation. So I already told you how qubits are different than bits, how our representation of them they seem weird, but it's only because we are used to thinking in classical terms. So the quantum way to see the world is just very foreign to us. And when this can be pushed even further when you do quantum entanglement. So correlations are just information that shares between two different things. Like if uh, if it's raining and I see it's raining and my friend sees it's raining, we both know it's raining. We have a shared information, and this is a kind of correlation. In quantum, you can do correlations that go beyond these things using this superposition. And this one of them is called quantum entanglement. This is really what powers quantum computers. Not superposition, it's entanglement. All the quantum algorithms that we know of depend on having quantum entanglement. In fact, quantum entanglement is known as a resource for quantum computation. So without good entanglement, you cannot do quantum computation. This is really what we spend things. And this is just to say you cannot do computing with one qubit. You need at least two, just the same as in classical logic gates. It's not very surprising. Just to give you some visual intuition, I want you to think again about what I was mentioning before about superpositions. That it is like trying to describe a 3D object in a 2D plane, and it's just incomplete. And that's why it's so puzzling about it. So if you then put two qubits together or two of these wireframe cubes, something really funny happens. Is that you still have the same effect with this wireframe, but once your brain chooses one to be a box, automatically your brain sees the other one as a box. Or if your brain chooses one to be as a corner, your brain also forces the other one to be a corner. This is a way like your brain is trying to make sure that your brain doesn't know which one it is. As long as it's consistent, it's okay. And quantum entanglement, you can think about it like that way. Is that when you have a superposition and when you measure one, you don't know what it is, but when you measure one, it determines what the other one is instantaneously, immediately. The other one is determined to be the same way. This is this is what's very puzzling, and this is why Einstein was really upset about it. He didn't like them at all. He was wrong, of course, about this because we use this entanglement. I use entanglement every day at my work, and it's a very powerful thing to use. But it is very counterintuitive. This doesn't break any like faster than the speed of light and those things. That is absolutely not true. These correlations are very special and very limited in some sense that even though I know what the other one is, I cannot use it to send information. So what we're gonna do now is to have a circuit to create quantum entanglement. And for that, we're gonna introduce our next gate, which is the C0 gate or the control not gate. This is the first 2-qubit gate. And you're gonna see this gate over and over and over in all the quantum circuits, along with the X, Y, Z, and Hadamard. The control not is a very, very, very popular one, very basic one. It's definitely like one of the first you have to learn. And this one, it's a bigger matrix. It acts on 2 qubits, and what it does is does an operation does a rotation on one based on what the outcome of the other qubit is, and so this correlates both. So to create entanglement, the circuit this is what it does. You have 2 qubits, and 2 classical bits. The first thing is you do a Hadamard gate on this qubit that was on the ground state was 0. The Hadamard gate is going to create a quantum superposition. Then this quantum superposition is going to be used to condition this NOT gate. And in doing so, it's going to create another quantum superposition and in a very special way that they're tied together in this entangled way. And finally, we're going to do measurements on them, on both of them, just to see if they always give us the same outcome. So for that, I encourage you again to go to here for whom the bell entangles, this example here. It explains a little bit about entanglement and introduces the gate and the circuit just like I did. And then you can go and run some code. I'm gonna go here to main. Okay, so let's look at what this this code is doing here. So first we have again the standard opening, chasm, and the standard libraries. Now we're creating 2 qubits because we need entanglement with 2 qubits, so we need to create 2. And we're creating 2 classical bits because we want to measure each and look at what they are. Then we do a Hadamard gate on 1 qubit. So this is we take it from the 0 state into a superposition. And then we do a control NOT gate between those 2. This is also called a C NOT or also control X gate. These are all equivalent names. And finally, at the end, we're going to do measurements on each of the qubits to see what they are. All right, so I'm going to run this. First, let's do it once. So you can see, again, it's a chasm, but it's a simulator by Strangeworks with a superposition. This looks the same. And we got the 0, 0 state. So you see when 1 qubit was 0, the other one was 0 as well. Let's run it again. Let's run it again, but this time take more, gets more statistics. Let's do, I'm gonna do 100 here. Click run this project. And what I want you to see is like half of the time you get 0, 0, and half of the time you get 1, 1. But you never get 0, 1 or 1, 0. This is because those 2 qubits are correlated. No matter what one is, the other one is going to be the same. And you can look at this table here, and you can see it's exactly that. See, when 1 is 0, you get 0, 52 times, roughly 50%. But you never get those 0, 1s and 1, 0. What I want you to do, though, is now that you know some qubits, you can add more stuff here. You can try to play with these things and add some rotations like this. Maybe add some rotations on the other one as well. So let's see, Y, Q1. And again, just save it, run it, and just start to play with this entanglement and see if you can mess it up a little bit. The idea being that it's you see now by doing these rotations, when 1 qubit is 0, the other one always is 1. When 1 is 1, the other one is 0. They're always opposite to each other, but you never get them to be the same. And I just did that by playing with this a little bit. And I encourage you to do the single gate things here at the beginning to really try to mess up with this entanglement and see if you can get other kinds of entanglement here. So you can also change the Hadamard for other gates. There's also other things you can do. And you can also do single qubit gates at the end. I'm gonna let you guys play for a few minutes, trying all these options. So just like I did some examples here before, here I did some here. You can also move this to the end and see what happens. So do some operations after the C NOT and run it again. The idea again, it really is that you start to get a feel for entanglement and how the rotations change things a bit. Of course, you still need to look at this in a lot. See, this one didn't do anything. That's very interesting. I want you to start playing with it just so you get a feel for I play with entanglement a little bit. And if you're really brave, you can put something in the middle, then add another one here, and really start now building 2 circuit gates. I'm gonna open again the floor if there's any questions and so on. But for now, this is an open-ended session, a few minutes, so you guys get to play with entanglement and build your own 2 qubit circuits. Yes. Are there any questions?
So it looks like the questions are already answered by Andrew in the chat.
Okay, great.
Are there any more questions from anyone? Actually, yeah. So this one question. So someone asked. Actually, this is more pertaining to the Rubik's cube before, but does this apply to any random scrambling, or is there a way to always get to zero irrespective of starting position, and naming a global solution with no brute force?
For the previous one. That's a good question. No. Each different scrambling, you have to come up with a different sequence of gates. In fact, some scramblings you might not be able to unscramble using the gates that I gave you. I had to be very careful designing to make sure that with only those four, you could unscramble it with those four. So I had to design the problem so it was easy. In general, that's actually a really hard problem. If it's a really random scrambling and nobody gives you any clue whatsoever what it is, it could be quite hard to find a good way to unscramble it. It's because we can never see the qubit directly. In which case, a smart strategy might be that you start doing a lot of experiments on these qubits. You try it many, many times, like just take a lot of statistics and you basically reconstruct what the qubit is. This is known as tomography. And then you can come up with the gates. So in general, it's hard. In that example, I made sure it was an easy one so you guys could like come up with a solution in a short time. Yeah. And while you guys play with that, I wanted to point out that in the library we have this getting started Bell-State post. And as you can see, it's for beginners, but it has a lot of different languages here. And this is basically, it guides you through how to create your first circuit and so on. But the interesting thing is that you can see how entanglement is built not only in Chasm, but in other languages. So this is just a good way to compare them. So if you click here, run code, you will see that we have the same example on Chasm, which you've seen. But if you want to see how that looks in Qiskit, you can see the same code here as well, and you can run it and just see how each of these different platforms build these things. You can use Jupyter Notebooks. You can use Penny Lane, which is a machine learning one, Google Circ, just so you can start comparing the code and how to create the same circuits. There's many ways to go about it. There's very different philosophies about it. You can tell that this is way more lines than Chasm, but also that one has more power, so it allows you to do more things. So this is also a very good one if you want to just get a feel to sample many of these languages and do the same exercise we just did with other languages as well. So it will be here in the library, getting started Bell-State. It's the same thing we just did, except for multiple languages. So you get a feel and you can code and play in different ones. Yeah. Mm-hmm. And are there any other questions, or if not, do we get moving?
I think there's one more question. So someone asked, if you perform a Hadamard gate on 0 and 1 before the CX gate, then you would have an equal chance of all 4 state combinations, but entanglement will hold.
I didn't quite follow. Can you send me that one? Can you try it? Send me that one to my account. So if you have a project here and you do share publish and you write Cesar as my username, click send invite, I should get it here and I can have a look of what you're trying to say. Yeah.
Yeah, and you can also post this, just have more discussion in the Discord chat later as well.
That sounds good. Yeah. That sounds good.
Yeah. So I guess we can move on to the next part.
Perfect. All right. So now we're gonna get to the crazier part of this talk, if it wasn't crazy enough, which is the power of one quantum algorithm. And this is where I want you guys to leave getting a sense of why are quantum algorithms like. What makes quantum algorithms more powerful? Like, right, where is the power of a quantum computer? This is a very artificial example, but it's very visual, which is why I find it very useful. And to set up the problem, this is a problem we're going to solve with classically and quantum, so you guys see how much better a quantum computer can be at some problems. So to set it up, I want you guys to imagine that you're at a bar and you're coming out of the bathroom, and maybe you had one beer too many, and as you're walking searching for your friend, you realize your feet are a little unsteady and like you cannot really see your friend, and you're squinting, and you're looking for your friend, and at this bar it's a punk bar or something, and everybody's dressed the same way, everybody's dressed in black, so you cannot really see who your friend is, and you just walk straight to the middle of the bar and stare at the person there, and then you, it's not my friend. Okay, so then you take a step to the left and you look at the person next to that one. It's not a friend. But because you're drunk, you forgot, so you take a step to the right and then look at the same person again. It's not my friend again. And you keep doing this randomly until you find your friend. That's one option. Or more likely, they call security on you because you're bothering everybody. Like, this is very annoying. And they ask you to please leave. And so this is known as the drunken walk or the random walk. And although the behavior of a drunk is very, very complex, we can model it mathematically with a very simple model, which is you flip at every step, you can flip a coin, and if it heads, the drunk goes to the left, and if it's tails, it goes to the right. Then it takes another step, you flip another coin, and at every step, you do a coin flipping. And this is a way to model the complexity of the drum card in a simple way. And now imagine that this is what you do. Imagine this happens one day, and then you go another day, and then the security guy sees you here. Okay, and the security guy happened to be a physicist, so he writes it down. Oh, last time after some time, I found the drunkard here. Next, the day after, he finds the drunkard here, and so on and so forth. It happens many times. And the security guy, he reaches two conclusions. One is you have a drinking problem, clearly, and two is that this behavior actually has a pattern. It's a Bell distribution. It is a normal distribution. And here I have a very simple example here, as you guys can see. So this is just the same. It's just with marbles, okay? And if I do it here, each marble goes randomly, but it fits almost perfectly this Bell distribution like that. And this is a very common phenomenon in the world. It's this Bell distributions, like standardized test, for example, is one that has that. And I'm not gonna go into like discussion of probability theory and like probability statistics. What matters now for you guys is the fatness of the curve. That's all you have to remember. Is how fat, how spread out this curve is. And this fatness is called the standard deviation. That's the name we're gonna give it. And if the drunk has taken n steps, the fatness is going to be the square root of n. So if the drunk took 9 steps, we say that the standard deviation, the fatness, is going to be 3, because square root of 9 is 3. If the drunkard took 100 steps, the standard deviation is going to be 10, because of the square root of 100, and so on. So just keep in mind that it's the fatness that we care about. It's how spread out. This determines how far away from the center the drunk could have been. When you have very few steps, this is very, very narrow, because the security guy knows the drunkard is probably going to be very close to the center. He hasn't had time to leave the center yet. As more steps happen, the drunkard is more likely to have start going farther and farther away to the ends of the bar. So the fatness captures exactly that. How much farther will the drunk have had a chance to escape? And okay, so that was the classical drunk. Let's get quantum drunk. Okay, we're gonna do the same thing, but instead of with the coin, we're gonna use a qubit. And remember that qubits, you can have them in superpositions. So when we have this quantum superposition, the drunk will also get into a superposition. So the drunk is gonna go both to the left and the right at the same time, every step. So this is like craziness now, right? If you see this at a bar, like, oh, that's a very, very, very interesting bar. So this quantum drunk is the same idea, but we allow the drunk to be in superpositions as determined by a qubit. And this is how this looks like. At every step, the drunk can go to 2 different sites, but when the security guy comes to look at him, he will only find them with some probability at one side each time. Although he's superposed between all, when the measurement is done, he's only at one specific place. And our security guy that happens to be a physicist by day, he of course keeps a tally, and gets its statistics. And he starts to notice that this doesn't look like a normal distribution at all. This is a really, this is not a bell curve. This is very, very strange. So this is what he concludes. It's like there's this the classical drunk, he has the bell distribution, and the quantum drum looks like this. It's like really like jagged and like all over the place. This is related to those waves from the beginning. Remember that I said the two waves interfere with each other? This is the same. Like the drunk interferes with himself in these superpositions. And there's some possibilities that are very low probability and some possibilities very high. And I like to think of this distribution as the vampire fangs because this looks like teeth to me. And something to notice is that while the classical drunks tend to be mostly at the center, the quantum drunk is not really so much at the center. He's most like farther away. And there's some spots that he's never there. And this fatness, this spread measure, the standard deviation, while for the classical drunk it was square root of n, for the quantum drunk it is n. So the quantum drunk is square times farther away. It squeezes out more to the side. It's than the classical drunk. If you have a quantum drunk friend, he's much harder to find. That's what this means. It's square times harder to find. And this is a big, big difference. This is keep this in mind. This is the main thing that you need to know to understand the power of quantum computing is this difference. Is that if classical is something, quantum is square times. It really comes from the squeezing of the probabilities like this. Okay, so remember this. This is like super important. This is where all the power of quantum computing comes from. Now we're gonna use this for a problem that we're gonna put the drunks to solve. So you see the power of quantum computers. All right, so let's get the drunks, find the exit of a labyrinth. So let's send the classical drunk. All right, very good. Classical drunk, you made it to the end. Let's have the quantum drunk. He goes into superpositions and he finds the exit. They seem pretty much the same so far, right? Like there's no big difference between them. However, not the structure of this labyrinth. This is not like a random labyrinth. This is a specially designed labyrinth. At the beginning, it forks every time. And at the end, kind of the forks come together. It is like two trees glued together. And this is how it's called, the glue tree. The labyrinth part really is at the beginning, in the middle, that I like randomly shuffle all this stuff. And the classical drunk spent a lot of time, bouncing around here in the middle, while the quantum drunk was going to all the superpositions everywhere. But both made it to the end. So far, we don't see any difference. But now, let's send more drunks to get some statistics. Let's start sending more drunks. So, we send some more drunks. They start making it to the end. And we send some more drunks. And notice the following, that the classical drunks tend to stay a little bit longer stuck in the middle than the quantum drunk. And this is because, remember, the quantum drunk spreads out more. It allows it to squeeze out of this labyrinth part in the middle. And that's really, really it. And in fact, for this kind of labyrinth, the quantum drunk is exponentially better at finding the exit than the classical drunk. And so this is a task where quantum computing gives you an exponential advantage if you have access to quantum resources than to classical resources. Now, this is not true for every possible labyrinth. This is really about matching this idea that the spread of the quantum drunk is always square times more. For some problems, if you code them properly, these square times you can turn into like a way bigger advantage, like exponential. And this is going to be true for every quantum algorithm that you have. Quantum computers are always square times faster than classical computers. It's just a little weird to encode it, but you can always get square time for free, which is pretty good, because that means if something will take you 10 days if something will take you 100 days in a classical computer, in a quantum computer, it might take you 10 days, ideally, things like that. If it's going to cost you $9 million in a classical computer, in a quantum computer, it will take you only 3 million when we have scalable quantum computer, and so on. So it's always square times better, the quantum drunk. But you can even do more forced problems with certain structures. And all quantum algorithm is really about understanding the structure of some problems and seeing if there's a way to use the spread in the right way to do a little bit better. You can always get square for free, but you can get better for some problems. Okay, so I want you guys to play a little bit with that quantum walk on the code. Let's see how are we doing time. Okay, so Here I have the code for quantum drunk. This is a very simplified walk, mostly because the circuit is otherwise very, very ugly and it's not so pedagogical. But this one walk only has 4 nodes. It's 0, 0, 0, 1, 1, 0, 1, 1. Think of 0, 0 as the starting place, 1, 1 maybe is the end place. And we have 2 qubits, and they encode the position. These are the positions. So 0, 0, 0, 1, 1, 0, 1, 1. Qubit, this other qubit here, Q2, this is going to be your coin. So you use a Hadamard to put in a superposition. This is flipping the quantum coin. And this is how the quantum step looks like, by the way. It uses the coin and resets it partially with this thing. And depending on this coin, the walker moves in some ways. And then we do some measurements. So what I want you guys to do is go to the example for quantum walks here, run the code. We'll do some statistics. So let's do 10. And you see the circuit again here. And you see that after 10, the drunk can be in either 0, 1, or 1, 0. So the drunk is now in superposition between 0, 1, and 1, 0. Let's do more statistics here, such that we get better statistics. I'm going to do 100 instead. That should get us more to 50-50. So the drunk starts at 0, 0. And after 1 steps, he is in a superposition of 0, 1, and 1, 0. So the drunk starts here, and then he goes to the superposition of these two. If you want to play with this more, I encourage you really to play with this code. Remember, this was the step here. I'm going to show you. Okay, so this is 1 step. Things that you can do to play is copy paste this code and copy and paste it here, so you do more than 1 step. So let me show you how that works. So I'm going to take this. This is 1 step. Copy, paste. We do 100 again. So, and let the drunk take another step. So it went from 0, 0 to then a superposition of 0, 1, and 1, 0. And now with the second step, it makes it to the end with 100%, and so on. However, I didn't put X's in this labyrinth. So if you do this again, the drunkard just leaves it just starts bouncing back and forth within the X and the beginning. So things I want you guys to do on your own is to play with this. Change this code, change the number of steps. Also change the initial step. Now you know all the basic 1 qubit and 2 qubit gates. Mess with them. Put the drunk different places. Maybe mess with the coin as well. Like change the superposition. See how biasing the coin makes the drunk behave differently. And we don't have too much time, so I'm gonna leave this open so you guys play with this one later at home on your own. It's what I would suggest. So you start to get a feel of controlling the drunk, messing with it, and so on. Okay. Are there any questions before I go to an overview of quantum algorithms?
So while we wait for people in the chat to come up with questions, I actually had a question. So in this case, how do you define, kind of the threshold where the drunk has found the exit? Well, in the simple 4-node example, like after 2 steps, you can get 100% probability in 0, 1. But yeah. Sorry, in the exit 1, 1. But then, if you have a complicated graph, and if I think about the drunk as a wave that's like kind of exploring the nodes, then it can what probability threshold can you define that the drunk has found the exit?
That's a very good question. So of course, if you put a very low threshold, let's say 5% probability, and I declare success, then all the drunks, classical and quantum both, they might be more likely to find the exit. If you raise this threshold to say like 90% of the drunk, like 90% of the wave function has to be here, like then it's different. But what matters is that as long as you're consistent with this, you will get this exponential behavior. The only thing that you're changing is the parameters for the exponential, but it's still exponential no matter which one you choose. So yes, you can change it, but it will always be exponential regardless. And this is something why for this example I didn't put exits and the beginning and the exit, because writing the code for that's a lot of complexity to how it works, and it will require a much longer seminar. Yeah.
Okay, so someone had a question. I'm not sure if this is phrased correctly. So, okay, it says, so the quantum path finding algorithm with at max, how many different paths at each point is possible?
So the quantum drunk, it looks similar to pathfinding, but it's not the same as pathfinding. But there are some pathfinding algorithms with different logic, because the drunk is not finding one path to make to the end. All that matters is he makes it to the end. It doesn't matter which way, and it can take many. The how many superpositions can the drunk take? It depends on the details of the walk itself, the network, and also of how you bias the coin and so on. And so all the details do matter. This is why I had to keep it to a very simple network here, because it's the only one that is very tractable, all these things. But this is an incredibly large area of research. So if you guys want to do some research, come up with crazy networks and start playing these games. It's very likely you're gonna find really cool stuff. It's just a very fruitful area, because it is very complex behavior, and not always you get exponential advantages, only in some structures of the network. And so this is an area where you can do a lot of things. And there's a lot of other tricks you can do, by the way, if you want to help the drunk out. You can sort of bias it to go forward more than backwards. You can and suddenly you will see that some of the advantages get larger and sometimes they get smaller. So all I have to say is that that's an excellent question. It's really, really big, and quantum walks, this could be like a whole semester class just on quantum walks. So just I encourage you to play a little bit with the small network, and then there's examples online. You can add them to a library and so on. So you can see for bigger networks and start to do these biases to see really where the drunk is for them. Yeah. So sorry, I cannot answer the question. It's just a very good one and a really, really big one. Yeah.
Okay, I think there are no more questions right now. Again, if you come up with any questions, please post them in the Discord channel afterwards. Yeah, so okay, then maybe we can move to the next part.
Yeah, so now we covered the principles of one qubit operations, how to create entanglement, how with one qubit operations and entanglement we can do a quantum algorithm, quantum walk, that happens to be exponentially better for some kinds of labyrinths. And now I'm going to give you a big overview of quantum algorithms overall, so you understand what we're talking about when we say it's more powerful than something. So I'm going to have a what I call the power category. Okay, so I will explain what this means in a second. So the lowest tier power category will be to have a programmer with a classical computer, like my phone or the laptop I'm talking through. So imagine like Bill Gates. I'm choosing Bill Gates because he probably doesn't code anymore, but he used to code back in the 70s. And for this category, it doesn't matter if Bill Gates is coding that computer for the 70s or if he's coding HPC Center. They're the same computer, even though it's ridiculous. We consider them to be in the same power class, as the fastest high performance computers now are the same as the tiny computer from the 70s that Bill Gates used. And these are, of course, classical computers. That's really what they are. This is the power class. So these are the kind of problems Bill Gates could attack given a classical computer. Like if these are problems he could solve using this tool. On the other end, we have problems like the traveling salesman problem. The traveling salesman problem says, given a network or given a network of cities, let's say, what is the optimal path for a salesman to visit each city once without repeating? So it's a very, very common point. It's actually a really challenging problem. This is a problem that you need to try every possible path, all the possibilities, all of it, to solve for sure. And it's actually really, really computationally hard. This is a problem a quantum computer could not solve. Classical computers cannot solve this efficiently. Even if you solve one network, if you have one more cities and some connections, it gets super hard to solve that one. And then even if you could do that one, you add one more and you have to do everything again. And it's like every time you add one more, it gets way harder, way harder, way harder. And these are problems that we think are basically intractable. Like given large enough, we will never catch up. There's nowhere you can have computers fast enough to beat this. And quantum computers, by the way, they cannot do them either very well. They can do some instances a little bit better than a classical computer, but it's still intractable for them. I'm representing this class of problems that are by this DC Universe character. He's called Destiny. He's Destiny of the Endless. and he is the representation of the destiny itself. And every time he sits somewhere, he sees all possible options that could happen in the world at the same time. And this is basically the kind of power you will need. You don't need a quantum, you need to see every possible option ever, every step to be able to solve this. Quantum computers cannot do that, by the way. They're great, but they're not that powerful. So this gives you two ends for the power spectrum. It's like one end you have Bill Gates in the 1970s. In the other one you have this bigger than this mythological creature that can see every possible option in the world. And then in the middle, we're gonna have, of course, quantum computing. So the first examples I'm gonna give you is some quantum computing algorithms that are quadratically faster. So these are square times faster. And this is like quantum search. So this is like Google search and so on. And some optimization problems, like constraint optimization problems, they are square times faster. This square times comes from what we were discussing before about the spread of the drunk. It really comes from that. And there's a lot more here. And I'm representing by Batman because square times is good, but it's not like super good. So I'm using Batman because he's like Bill Gates. He's a human. He has no powers. He's a billionaire too. He is clearly better than Bill Gates. Like, this is no doubt about it. No matter how hard Bill Gates try, he could never be Batman. But Batman does not have superpowers. He does not. This is clear. We don't think Bill Gates could ever be like Batman, but Batman has no superpower. Batman is human. And this is what we think about this class of problems. It's quadratically faster. Quantum computers are better, clearly better than anything you can do, but they're not superpower. And then we have all these other superpowered beings here. So for this kind of problems, on this end, we have the Wonder Woman, Superman class of superpowered individuals here. So these are the ones that if you have an alien invasion, if the sun is gonna explode, this kind of thing that you want Superman and Wonder Woman. Batman can help a little bit, but you want one of those. It's like these are way harder problems than this. And clearly we have a sense that Wonder Woman and Superman, they are superpowered in a way Batman is not, and they're like way more powerful than them. And so this is like this extreme class of quantum problems. And for example, some of them are quantum factorization. This is what people say, oh, quantum computers could break existing cryptography, which is true, but also quantum technologies can bring us better cryptography. So ultimately, privacy is guaranteed for us. But there's also some chemistry problems that are like that. And for example, finding the energy of a molecule is actually a really hard problem because it looks a little bit like a network problem with all these electrons connected to each other, except it's quantum. And every time you add one more electron, it gets exceedingly hard. And this is a problem that classical computers are really terrible at, because you have to take the quantum problem, map it to a classical computer, which has a lot of approximations, evolve it, which makes the approximations go crazy, and then map the problem back to the quantum solution. And now by the end of it, you have big errors. In a quantum computer, you can take quantum molecule, put it in the quantum computer directly, boom, simulated. These are problems that quantum computers are really good at. If we had a big quantum computer, this is like Wonder Woman, Superman level stuff that will have a big impact on how we study pharma, for example, understand these things. And below these levels of chemistry and so on, we have like Aquaman level problem. So there are some chemistry problems that are not super powerful, but we can do with like less resources in quantum computers that are still like way better than anything we can do before. And I'm putting Aquaman here because everybody makes fun of Aquaman with his dolphins and all that. But in the end, if he's underwater, he actually can punch as hard as Superman. So he's pretty good, just has to be in his element. And this is the same for some of this intermediate class of problems that we have. It's think of it Aquaman problems. There's some chemistry problems that fall here. And then we have quantum machine learning, which is like super exciting, super popular problem. And we don't know where to put that one in. We have no clue. And so it's just a very broad class of problems. It doesn't quite make sense to do comparisons and these power checks. And I'm representing this one. And what we do is comparisons. We run stuff on quantum machine learning. We compare it to the best known classical machine learning and see how better it is. But maybe somebody comes up with a better classical solution. We don't know. It's a lot of experimentation, very fruitful area for you guys to go code because it is very experimentally based and you can learn very cool things that way. And I'm representing this by John Jones. He's also known as the Martian Manhunter. He's also part of the Justice League. with like Batman and Superman and Wonder Woman and all those guys. But nobody really knows how powerful he is as a superhero. Sometimes Superman has even said like he could be more powerful than Superman, but we don't know. We haven't never seen him. So I'm putting here like question mark. We don't know where he lies in this ranking. And then here, this is a class of problems that you might have seen in the news a lot. There was some reports a few months ago from a Chinese team that achieved what's called quantum supremacy, and Google had done it some years before. And this is basically can we come up with one problem that is so hard that no actual HPC center in the world could solve it now, but that a quantum computer could? That's really what quantum supremacy. So it's not like build a good quantum computer. It's more like let's come up with a terrible problem for the classical ones that a quantum could do it. And of course, this problem is very artificial, right? Like it's like touching your nose like this and stuff like this. It makes no sense. But it is important for the following reason. It's because if with this quantum supremacy experience, what people are doing is to show that in practice, these quantum computers are superpowered. Like this is not like Batman. This is something that's beyond anything any human could do or any classical computer could do. That's really what it is. So I'm putting them here at the very edge of this. So it's like, they're not so great, but they're definitely a superpower in a way that Batman is not a superpower. And the point of this algorithm is nothing but to show that we can have quantum computers right now that are indeed more powerful than anything else in the planet. And so those are the claims of all these experiments. There's been 2, and I'm sure you're going to see in the news more and more and more of this as new technologies come up. Keep in mind always that these problems are not very useful. These are just to show off they can be. So for this, I'm choosing this as the superhero I'm choosing to represent it. It's called Stoneboy. Stoneboy, it's often, if you look him up, it's often the most useless superhero in the DC universe. So his superpower is that he can turn into a stone statue, and that's it. He just stays like a statue for 6 months. He just turns into a statue. He cannot fight as a stone. He's just a statue for 6 months. So is Stoneboy superpowered? Absolutely. There's no doubt that Stoneboy has superpower where Batman doesn't. Is Stoneboy useful? No. We want Batman. I'm going to have Batman because he will help me out better. But it gives you the idea. This is really what we're trying to achieve with this kind of experiment. And you will see them a lot more in the news. There's going to be more claims. And little by little, some of this, they're going to start becoming more and more useful when we have real practical applications for quantum computers. Okay, so we're running out of time. I have written another example for you guys. This roll with the demand. This is an optimization example that you can think of as like vaccination storage, or the example we have there is a little silly with like toilet paper storage. But you get the idea. I want you guys to go play with it. Okay, and to wrap things up, I just wanted to say that Strangeworks, what I show you today, what you're using is the public open source community, which we call the QC. And this account is for free. It's for you. Use it, run all this stuff, give us a lot of feedback. You know, when you do some cool code, post it on Twitter with the link, all that stuff. Use it for this hackathon. Really use it. This is for free, and it's going to stay like that. The idea is to foster an open source community of people like you guys learning and using tools. But also we learn from the requests we have. A lot of the features requests come from users that we have. And at Strangeworks, of course, we have the other side. That's the way that pay the bills, which is from the users, from what users ask us to do, the tools that they like, and so on. We have a beefed up version of that for enterprises that we sell, and with like user management and so on. And so the way we see it is that we're very early. We want the community to play with these things. So where are things in quantum computing? I want you to like walk away with this image. This is ENIAC. It's the first computer. This is where we are, where you had to know a lot of stuff, and it was very hard to get access to the computer, and it was very technical to get things running. This is where we are now. Back then, to get access to a computer, you had to basically beg, and it was very limited time. It was very hard. In quantumcomputing.com, what we're trying to do is really change that. It's that imagine if back in the day when the first computer, we already had social networks and sharing and so on. Of course, we didn't have them because we're not computers. But imagine we could source this community to help understand the computer better and improve it and come up with better tools. This is you guys. This is really you guys. The way I see, like, who's the quantum developer, is you guys doing this, learning and so on. Use the community. It's open source, and help everybody improve these tools and give more access to quantum computing. And the last thing I want to answer is when is quantum? And I would say quantum is now. This is really the time for you guys to get started and start playing with the code and start doing useful things with quantum computers. And again, on Twitter, you can find me on -2fish or Strangeworks account. You can send us an email to goquantum@Strangeworks. And please send us feedback. We really appreciate feedback to mature this open source community. A lot of the features we have are from users like you guys. Okay, and with that said, I open the floor for questions.
Okay, so yeah, if you have any questions right now, please feel free to post them in the Twitch chat. But I think, while we're waiting for the questions, I think let's give a round of thanks to Cesar and Andrew. I think the slide design and quality was definitely like one of the best we've seen so far, and I think the audience was loving the superhuman analogies.
Thank you guys. Thank you guys for inviting us. And I forgot the time, but tomorrow I'm going to be part of a panel where we're going to discuss like everything about quantum enterprises. If you have questions about how did I get into quantum computing, or how can you get into quantum computer, where things are, that would be a great place to ask these big questions.
Yeah, I think because there are a lot of students here as well, who may be interested in like things like internships, or after they graduate, they might be interested in looking for jobs. I guess one question would be, can you tell us a little bit about like Strangeworks, whether there are any opportunities available for students, or postdocs and things like that?
Yes. So we are a 50-person startup. We're in the process of growing and so on. So please do get in touch through the email gostrange@strangeworks.com, or just go to our webpage. You'll find our email, and by all means, reach out to us. As we grow, we're gonna have opportunities, and we would love to have great people like you guys being part of this.
So someone asked, just out of curiosity, where do you see the most potential on the hardware side?
Yeah, this is the question everyone wants to know. It's like which horse is winning the race, and the answer is, first, we consider ourselves Switzerland as Strangeworks, and we want to be very neutral to everybody. I don't want to decide, because every time I'm liking one, then something new comes up from somebody else, and then I like that one more, and then it could be that I say something now, and in a month it's gonna change. However, with that said, what I believe is that it doesn't matter what my opinion is, which is the best one, because each one is good and bad in different ways. They're all very special, and none of them are like amazingly like great. We're not at that stage yet. But what I do believe is that what matters in the end is usage. It's users like you using it. It's not gonna be my opinion. It's not gonna be some business article saying this is the best. It's what people embrace. The same with languages and hardware. And this is why we're doing this. The open source community at Strangeworks is to help everybody do this, like have more people using it. So you guys vote with your code and your clicks on the keyboard, which one is the best. And so stay tuned to the Strangeworks platform as we start to unveil more and more hardware, so you guys can play and you guys can choose. And hopefully at some point, maybe in a year from now and so on, we can tell you which ones are more popular, what people are doing in them, and like, general questions and so on, which I think ultimately is what matters. Is that, as you know, in the history of computing, often the numbers and the metrics don't matter so much as a lot of other things. So.
Okay, and so someone asked if the slides will be available. So we will definitely have the videos available, and for the slides, we'll double check with all the speakers for this talk and also other talks afterwards. And then if they are available, we'll find a platform to announce to everyone.
Yes, perfect.
And then, so someone also asked, do you think in a few years, almost every industry will need quantum programmers?
I think a lot of big industries are gonna be dramatically changed, needing quantum developers in some years. Absolutely, absolutely. I'm not saying that my mom will use quantum computers in 5 years without knowing them, but for sure, a lot of the big industries, they're gonna feel the crunch. They will wish they had switched to quantum earlier. That's what's gonna happen. So you guys are in the ideal position to take advantage of this in the market.
Yeah, so I think one of the things I heard the other day was that one of the biggest, like, kind of like, there are lots of great startups, including Strangeworks and, some other hardware, both hardware and software startups. But one of the hottest, like, kind of thing to do these days is to make quantum computing consulting companies that kind of
Yeah.
explains all the quantum computing concepts to, finance and,
Yeah.
like aerospace and other companies. So yeah, everyone's trying to get a foot in the door in quantum
That is correct.
computing.
That is very correct. Yeah.
Yeah.
That's true. What's his name?
Okay, so someone asked okay, so I guess this is going back to the quantum drunk exploration problem. So if we change the path on which people are walking, the way to the exit, the classical drunk will slow down to great extent and most of them won't get to the exit. But will it affect the quantum drunk people who are in superposition?
Yeah. This is a great question. So the exponential advantage, it works for a particular class of labyrinth. The one I showed is glue tree. If you change the labyrinth dramatically, you can bias it against the quantum drunk, more in favor of the classical drunk. You can really change everything to play all these games. All this is valid depending how you change it. You can slow down the quantum drunk so it's not quadratically exponentially faster anymore. That's very hard. Also, you can make it very difficult for the classical drunk to even find the exit. Like, this is true. And depending on the problem, like, it might be very, very biased or very, very hard or so on. The answer is yes, it is possible, and a lot more too. Like, and this is a very fruitful area of research. And I encourage you guys to play and lab. In our website, when you find examples, you're gonna see some of the basic resources for quantum drunks, for quantum walks, and just look at the references. You'll see that this is like a whole universe of people testing these things out. The reason why it's such a big thing is that actually I didn't mention this, but quantum walks by themselves, it is a possible way to picture quantum computer that's not just with the circuits. So there's like a mapping of quantum computers to quantum walks very directly. So this means that a lot of the complexity of quantum computers, they're still present in the quantum walk. Like, it's just very rich. So it's a very rich area of exploration.
Right, and I think in a similar vein, there's another question asks, can we improve the quantum drunk problem by discarding the state we previously visited?
Yes. That's a really good question. So this is the example I give you. Of course, is very simple because it's very visual. But it is a little silly problem, because if you think that the drunk remembers he was there and doesn't go back, even the classical drunk can be very efficient, right? And then there's people that actually play those games. It's like, okay, the drunk kind of remembers a little bit, but not too much. And there's like, this is like even further exploration of all the possibilities. But absolutely yes, if the drunk remembers he was there and doesn't go back, and the problem changes quite dramatically, and some of this advantage becomes smaller. This is true. And again, but you can then again come up with other ways to define the problem. So yes, this is a very good observation. And again, it's the whole world is a quantum walk. So there's a lot to discover there. Yeah.
Yeah, I think so. Those are very great questions so far. So I think if there are no more questions right now, we can thank Cesar again. And
Thank you, guys.
again, I want to remind everyone, please feel free to go to the Discord to socialize and also post questions if you have any after the talk. And yeah, so thank you, Cesar, for a great talk. And thank you,
Fantastic.
Andrew,
Thank you
for
guys for
helping
organizing this.
in the chat.
Yep.
So yeah, we look forward to seeing you in the panel tomorrow then.
Okay. Fantastic. All right.
Okay.
So
All
see
right.
you guys tomorrow.
Thank
Bye.
you. Bye, guys.